So I want to encourage you folks to do these odd numbered exercises out of the textbook. Based on some conversations I've had with some people, I don't know how many of you are, but I know there's a few that are not, and I think this will help you learn the material, and it'll help you complete the open math work, and it'll also help you do better on quizzes and tests because you'll have some stuff written down. So I picked some problems out of the chapters, chapter 6, and we'll see how it goes. So this is from section 1, where we're talking about the uniform distribution. So what I know about the uniform distribution is that it's like a great big rectangle, and they're telling us for this one that the peak rush hour has wait times of 10 minutes. So we know it's uniform distribution, it's 10, and we could break this up by the minute, and I don't know if I'm going to split this up exactly right, but if I do this by 1, 2, 3, 4, 5, yeah, I didn't do this quite right, 6, 7, what if we cheat? I don't know if it'll let me erase it. Let me try it. Oh, it will. So 8. I'll add 2 more rectangles. Now these are supposed to be equally spaced. Okay, so uniform distribution. So what's the random variable? It's how long I have to wait during peak rush hour in minutes. So now they want me to find what's the probability of waiting between 2 and 5 minutes. Well, 2 to 5 is that rectangle area. Pretend those don't go above the line. Well, the other thing we haven't done is, I know that the whole area, the whole rectangle is an area of 1 because it's a probability, right? So if I divide it by 10, that tells me each one of these rectangles, little rectangles, is 0.1 high or 1/10 high. So what's the probability of waiting between 2 and 5 minutes? Well, that's 3 wide by 0.1 high, so 0.3. What's the probability of waiting between 7 and 10? Well, again, between 7 and 10 is 3 wide by 0.1 high, so that's also 0.3. And what's the probability of waiting 8 minutes exactly? Well, 8 minutes exactly. Well, how wide is this? Well, how wide? See, if they aren't saying between 8 and 9, they're saying exactly 8. So how wide is this? Well, isn't that really skinny? Infinitely skinny? I mean, I really don't know. I mean, if you think about geometry, a point has no width or height, but it's there. So I'm going to use that same kind of thinking here, and this will pay off for later on. The probability of waiting exactly 8 minutes is basically going to be a very small number times 0.1, which is basically 0 is what it goes to. Okay, so I hope this without being any kind of width, that's going to have a probability of 0. So try number 2. It's similar to this. And honestly, the uniform distribution isn't all that big a deal. So it's random numbers have a uniform distribution. There's some other things to do, but that's where we're drawing from. It's warm up for what's coming next. So our textbook does a lot with a graphing calculator and doing that. If you have a graphing calculator, take a look at it. It works really slick. I'm going to show you how to use another applet. But even if I'm going to use a calculator or an applet, you definitely want to make a little sketch. Put 0 in the middle because that's the standard normal distribution. The mean is 0 standard deviations away from the mean. And then we want to know the probability of some random variable, some event. What's probability again? A z-score that's less than 2.36. So that's this area here. And that's what we're looking for. Now there's a lot of applets, a lot of normal curve applets out there. If you Google, the one I like, and it's once in a while my open math doesn't like it because there's not quite enough decimal places. But if you Google David Lane and then make sure you include normal, the word normal, you'll get taken right to that applet. It shows you a bell curve. I'm going to do some screen captures to show you. Make sure you include the word normal. If you just Google David Lane, you're going to go to some white supremacist website. Okay, so make sure there must be some Nazi out there that's named David Lane. Okay, so what we want is this, at least enough of Dan LeMay's attitudes. So we want this probability. Okay, so let's go out and grab that picture from that website. So here's the screenshot using that David Lane applet, and I actually included the URL with my screenshot, just so if you can't find it, you could copy that down and enter it directly. So here's the similar sketch to what I had, but so what I'm going to do is I want area from a value, because I know the z-score. I want to find this area. So I had a mean of 0 and a standard deviation of 1, because this is the standard normal curve. And I said below, remember how I wanted z is less than 2.36? So I said below 2.36. And then I clicked recalculate just to make sure. And what did it give me for a probability? Oh, almost 1. And if you look at that, that area is almost the full area. Okay, so make sure you have area from a value. Your mean, in this case, is 0. Your standard deviation, in this case, is 1, because it's the standard normal curve. And I made sure I selected below the number I was interested in. So then for the next one, let's see here. Whoops, I have to bring back my picture. Here we go. So now I'm looking for the probability of getting a z-score that's bigger than 0.67. So I'm looking for greater than 0.67. So if I add in that screen capture that I did of the applet, I'm getting a probability of 0.25. Notice I had area from a value, and I said above this time, because I'll be looking for above 0.67, and then that's the probability, about a quarter. So that's telling me that 0.67 standard deviations is about what the quartile is, the upper quartile. That's an aside. Okay, let's do the next one. Let's see, what do they want us to do? Between 0 and 2.11. So let's see. So I'm looking between 0 and 2.11. So I'm going to guess this is pretty close to 50%, not quite. And if we add the picture in that I did already for this, so notice how it cuts it off at 0 and stops it at 2.11, and then that's the probability, 0.48, so pretty close to 0.5. So last one, remember, area from a value. Last one, we want to be between, 0's in the middle. Notice I'm always putting that mean in, negative 2.78 and positive 1.97. And I want the area between them, so I'm going to do between two z-scores. So, and here you'll see, I said area from a value between those two z-scores, and that's the probability. Almost 100%, not quite. So this is fairly straightforward. I'm going to just do the setup. You can always look up the answers. So remember, a z-score formula is the measure we're looking for. Get a z-score from, I'm going to subtract the mean, and we're going to divide by the standard deviation. So we've got a measure of 23 minus 25 over 3, which is negative 2 over 3. So we could change that to a decimal and say that it's about negative 0.67. Next one, we're going to do 33 minus 25 divided by 3, because the standard deviation is still the same. So that's going to be 8 over 3, which is about 2.33. Then we're going to do 19 minus 25 divided by 3. So that's what? Negative 6 divided by 3 is negative 2. And then 45 minus 25 divided by 3. So this is for the last one. So that's going to be 20 over 3, which is 6.33. A very large z-score. So this is about the length of Atlantic cod, and so our Raynham variable is exactly it. What's the length of a randomly caught fish? They tell us the length of fish is normally distributed, so that means we can apply this normal curve, these normal curve ideas to it. And what we have is we have a normal distribution. Remember, shape is normal. The center is the 49.9. And we've got the spread. Because it's symmetric, we can use the standard deviation. And let's see, what's the probability that we catch a fish that's less than 52 inches long? So 52 is to the right of the mean. And we want to know the probability that it's less than 52. So that means we're looking for this area here. Let me go to a marker. We're looking for that probability, that area there. And here's the Applet result for that problem. I noticed I put the mean of 49.9 in the middle. I said the standard deviation, and I said below 52. And again, it's error from a value. Okay, same as with the standard normal curve, except now the mean's not 0 and the standard deviation is not 1. So then the next one for part C, we want to know the probability of a fish being caught that's longer than 74 centimeters long. So go to that applet, and notice I got the same parameters. I got the same mean, same standard deviation, error from a value, and I want to know above 74. And if you look at, one nice thing about this applet is there's the mean, it adds the standard deviation, adds another standard deviation, and then it doesn't show us the third here. But so it's basically like the 68, 95, 99.7 rule setup. It's interesting that shows it's minus 3 standard deviations, but not positive 3 standard deviations. But anyways, so I'm going to ask you this: how do I fill out? How do I get that third number up here? I hope you remember that we're just adding the standard deviation, right? I'm going to add 3.74 to the last one, and that just on this side we subtracted it. So anyway, so what's the probability? Well, I see that, so that's around 60, 61 will be that last number, that third plus 3 standard deviations. And we know that plus or minus 3 standard deviations will catch 99.7% of the distribution. And since a score or 74, a length of 74 is way outside that, there's almost no chance that that's going to happen, and that's what this applet's showing us. Okay, hopefully you're making that connection. So then for the next one, same as before, except we want, let's see, in between the probability of catching a single fish. It's between 40.5 centimeters long and 57.5 centimeters long, and we're looking for this area right here, right in between those two. And for that applet setup, parameter is the same, area from a value, and I just said between 40.5 and 57.5, and that's this area here. And there it is, almost Almost 98%. And that kind of makes sense. If we know there's 95% of the distribution will fall between two standard deviations, it makes sense that that little bit additional will be will make up the extra 3% or so. Maybe there's a little bit on the side too. Okay. So to answer your question E, suppose I did catch a cod that was that long. What does that mean? Well, I know the probability of catching a single fish that's long is practically zero. So there's two things I can conclude. This is a very extreme, rare size fish. Very lucky. We probably should just catch and release it because it's so old. Or the other issue that we could consider, and this is where we're going to go next week, is that this mean might not be right. So there's two ways we could go with this. I mean, just the luck of the draw to catch a fish that large, or as I said, the cause in a question, maybe this isn't right. But more with that later. So this very last question causes us to change gears a little bit. It says, what length are 15% of all Atlantic cod longer than? So I know the mean's 49.9 still, or at least I'm assuming it is. But I don't know this X number. I do know that this probability is 0.15 or 15%. So I've got to find that X. So in the book they talk about with your graphing calculators you can use inverse normal. And you tell it, if you're going to use a graphing calculator, the graphing calculator is always looking for the area to the left. So I need to use 0.85 as my area to the left. So you'd use 0.85, comma, the mean's 49.9, and the standard deviation is 3.74. And we can do a similar thing with that applet. But one nice thing about using the applet is I don't have to worry about finding that 0.85. So you're going to change this applet to value from an area, because I'm looking for an X value when I know the area, or a Z or whatever. I'm looking for the value in the distribution. And since they are telling me 15% is greater than that, I just use this 15%. I put in the mean, the standard deviation, and I made sure to select above. And that's the number. I catch a fish that's 53.776 centimeters long. That's the measurement that cuts off the top 15%. Okay, you could have typed in, I could have typed in 0.85 as the area and selected below, and it would have gotten the same result. Okay, so that's how you use the graphing, use this applet for this inverse normal thing. Make sure you select value from an area when you're looking for a number and you know a probability. Okay, I skipped over doing the exercises of 6.4 because I've got that other video online and it's just using that spreadsheet and making a decision. So let's jump right to 6.5. So now what's happening is we're no longer just talking about a single individual. Now we're talking about sample sizes. And I hope you watch that Mr. Nystrom video or the one I linked to about sampling distributions. And we know that well, they aren't telling us what this is, but there's some random variable is not normally distributed, but it is mound shaped. So that's telling us it's symmetric, right? And unimodal. Now, for sample of size 10, I probably ought to go look at the answers and see what they're saying. But here's what I'm saying. Here's what I'm thinking. We don't know that the parent population is normal. Okay. In fact, they're telling us it's not normal, but they are telling us that it's mound shape. And if you think about that applet that I showed you, what happens with as it's drawn samples. What happens is the shape of the sampling distribution could be somewhat normal. It won't necessarily be exactly normal. It's starting to approach it, but we can't say for sure what it's going to look like because that sample size is awful small. It's 10. The conditions that you're going to worry about is to satisfy the central limit theorem for sample means is that you have to have a normal population, or your sample size has to be 30 or more. Then you start getting a normal sampling distribution. So can I say what shape the sampling distribution of the sample mean is? Not really, because it's not normal and the size is too small. For a sample of size 10, state the mean of the sampling distribution and the standard deviation of the sample mean. Well, assuming that we can use the central limit theorem, and really we can't, because this doesn't quite satisfy it, but I'll go over it anyways. So if we think it's somewhat normal, I don't know. I'm still hesitant about that. I'd like you to go look up the answers in the book and see what they're saying. It has a mean of 14, probably, but again, it's questionable because we're not meeting the conditions. And the standard deviation is always you take your old standard deviation for the individual or for the population if you have it, or you use your sample standard deviation, and you divide that by the square root of the sample size. So we're going to do 3 divided by the square root of 10, and remember that the square root's this symbol here, not the squared key, right? You don't want to raise to the second power, you want to take the square root. So that's the square root of 10, and then I took 3 divided by the square root of 10, and that's the standard deviation. At least it should be. I mean, again, the conditions we aren't meeting here calls us all into question. But then for part C now we can start working with this because we're meeting that condition. We know it's not normal, but we've got that sample size that's greater than 35. So we're good to go. The central limit theorem applies. With the shape is going to be normally distributed. We know it's going to have a center of 14, and it'll have a standard deviation of this. Notice I'm talking about shape, center, and spread. And I don't really want to use the median and the quartiles. However, the median is the same as the 14 because this is a mound shape, a symmetric distribution, normal actually, because of the central limit theorem. Okay, so that's where we're going with this. So remember, it's the standard for sample means. You take the standard deviation from the population or from your sample, if that's all you have, divide that by the square root of the sample size. And that's the new standard deviation you're going to use. So here we go. Number 3. The Raynham Variable. It's the average salary, or the mean salary of all the mean starting salary of all nurses, and that's what we're finding. That's the Raynham Variable we're measuring. So what's the mean of the sample means? Well, that is asking me because this is a sampling distribution. I've got 42 nurses that I've got salaries for, so it's a sample. The mean will be, well, actually, the shape of the sampling distribution. Let's answer this backwards. Okay, the shape is going to be normally distributed because this is a sampling distribution. The mean of the sample means is going to be that one, is going to be the national average. And all these samples of size 42 will fall around it. Remember that pile of X bars? That, here's our mu, here's our population average, and then I'm going to have all those X bars, all those samples of size 42. We're going to take them in all the possible samples and calculate those sample averages, and those will make a pile around that's symmetric, that's normal, around that population mean. Okay, and so what's the standard deviation? So how do those samples vary? Well, we know that it's going to be the old population standard deviation divided by the square root of the sample size. And there's this standard deviation for the sampling distribution. So we've done A. It's the average starting salary for 42 nurses. The mean's the same as the population mean. The standard deviation is this. We know that it's normal because of the central limit theorem. It's sample size is over 42. So now we're going to do some probabilities. So find the probability. So find the probability that the sample mean, that if we go out and take a sample of 42 nurses, what's the probability? 694. That we're going to get a sample mean that's $75,000 or more. So we're looking for that area to the right. So I calculated, I went out and used that David Lane applet, and I told it what's the mean, what's the standard deviation with these sampling distributions, what's the probability that I'm going to get a sample of 42 nurses with an average higher than 75,000. Well, the applet says 0. Why? Well, if we think about if I go up 3 standard deviations above the mean, I'm at 72,000. So there's only a point, if you think about the empirical rule, there's only a 0.15% that being more than 3 standard deviations above the mean. So the applet is telling us 0. Well, that's because there's practically zil chance that I'm going to get an average of 42 nurses with that high an average. A sample of 42 nurses with that high of an average. And the next question, how about for 60? It says what's the probability of getting a sample of 42 nurses less than 60,000? Well, 60,000 is below the bottom 3 standard deviations. So again, that's going to be 0. So that's how that works. And then what if we did get a sample of 42 nurses with an average of more than 75,000? Well, it's two things. It's an extremely rare event, and we were just, I don't know if we're lucky or unfortunate how to look at it, that we got a sample like that. Or the other thing we could argue is that maybe this $67,000 figure is not correct. I mean, maybe it's changed since 2013. You know, there's some other issues going on here. So those are the two things you can conclude. So that's the last of the original examples out of the textbook. At least the odd exercises. I mean, there are other ones you can do to get some practice. I encourage you to maybe try some of the even exercises. And once you've done this practice, go try the MyOpen Math exercises. They're pieces and parts of all these. They're not all put together. My thinking is that I want you to do the practice out of the book, and then the graded thing is the MyOpen Math. It's kind of like a pre-quiz quiz. So that's what I'm encouraging you to do. Hope this helps.